They just end up full of spam, so.
I know they're off.
All right, 2.6. All right, so we're going to talk about matrix inverses today. So before I talk about matrix inverses, before I do it, I want to read you a little passage from the textbook, a motivating passage. So, all right, here it says. Not that. Okay. Passage is as follows. Before proceeding any further, we give a word of encouragement to the more applied-oriented reader. It will probably seem at times that the ideas we are introducing are rather esoteric, and the formalism is pure mathematics. However, in addition to the inherent mathematical beauty of this, the ideas it incorporates pervade most areas of applied mathematics, particularly engineering and mathematical physics, where the problems under investigation are very often linear. And I will add, and if they're not linear, you make them linear by using derivatives so you can use linear algebra. So this is a hammer and nail problem we're dealing with here, right? Linear systems, what the tool set we're learning right now is very useful because we can calculate with it and because it produces reasonable models for nature and reality, right? Scientific things. So it's going to seem like what we're doing doesn't have any connection to anything as we go through the chapters that we're in right now. I will try to point out as much as I can where that happens. Just hold on to it because what we're learning is it's like when you learn to read, you start with the alphabet, right? You don't read books. You learn the alphabet first. Then you learn how they form words. That's kind of what we're doing. We're building the foundation for the way this language is used in all your individual fields. Okay? So just hold on. Because we haven't even gotten bad yet. Just what the real abstraction happens in chapter 4. All right, so the idea with matrix inverses is that we are trying to do the following. So first, observe that if we have two n by n matrices, so square matrices, so that if we have A and B both n by n, then A times B is also n by n. Square matrices kind of act like numbers. I can multiply, I can add them, I get the same kind of thing back again. I can multiply them, I get the same kind of thing back again, right? If I have square matrices, they interact with each other sort of similarly to the way that numbers do. And what that means is, if we have a system of equations that has a square coefficient matrix, if I have something like AX is equal to B, where earlier we were looking at the augmented matrix AB, where A was the coefficient matrix and B was the right-hand side, it would be awesome if I could use algebra to solve this equation. So what I mean by that is, if I gave you numbers, 2x is equal to 6, you can solve that equation for that unknown x by multiplying both sides by the inverse of 2. And then the inverse of 2 times 2 is equal to 1, the multiplicative identity. So you get 1x is equal to 2 inverse times 6. And so x is equal to the inverse of 2 times 6. And it would sure be nice if we could figure out what the inverse of 2 was. Well, with numbers, that's easy because you just take the reciprocal, right? X is equal to 1/2 times 6, which is equal to 3. So I would love to be able to do that same move over here. I would really like it from a theoretical perspective, an algorithmic perspective, and a computational perspective if I could find a way where if there was an object called A inverse that undid A, I could multiply both sides of the equation by A inverse, and then these guys would turn into whatever the matrix version of the number 1 was, and they would disappear. The answer would be something like x is equal to A inverse B. This would be sort of like the matrix version of division. You can't divide by a matrix, but you could multiply by its inverse if it had one. So that is the object that we want right here, this thing A inverse. So what we're going to start with is we're going to define this. This exact behavior is what we want to define. I'm going to start by reminding you guys that the matrix I, so recall, the matrix I, which was the identity matrix, was a diagonal matrix that had all 1s on the diagonal and 0s everywhere else. So that was the matrix that had a 1 and then a whole lot of 0s, and then a 1 in the second, a 2-2 spot, and then a whole lot of 0s, and then a 1 in the 3-3 spot. And you keep going until you get down to a 1 in the lower right-hand corner, 0s everywhere else, right? 1s on the diagonal, 0s everywhere else. The reason that we called that the identity matrix, because it plays the role of the number 1. If A is n by n, and I multiply it by the n by n identity matrix, I get A back again. So the natural version of the number 1 for matrices is the identity matrix. And just like over here with numbers, once I know I have a multiplicative identity, so with numbers the idea is 2 times 1 is equal to 2, and that means that 1 should be equal to the inverse of 2 times 2. I can take the identity operation and reverse it into an inverse operation. I'm going to define the inverse of A to be the object that when I multiply it by A, the matrix version of 1 falls out. So this is going to be our first definition. And then we'll track through some of the consequences of that definition. Definition, given a square matrix A the inverse of A, which is denoted A inverse, is the matrix satisfying A times A inverse is equal to A inverse times A, which is equal to the identity matrix. So if I start with the matrix A inverse is a matrix I can multiply it by on either side and get 1 out. Again, what you should be thinking with the identity matrix, it is the matrix version of the number 1. So I guess the first thing I'll demonstrate here is that something actually has an inverse. So I'll write down a matrix and its inverse. So as an example, you can think about the matrix A is equal to, got a nice example here, 1, minus 1, 2, 2 minus 3, 3, 1 minus 1, 1, and B is equal to 0 minus 1, 3, 1 minus 1, 1, 1, 0 minus 1. It's going to turn out to be the case that if you go through the hassle of multiplying these things, so if you actually calculate times this, so if you want to do this by hand, remember that you're going to calculate this product by taking the rows of the first matrix and producting them by, well, that's an interesting version of number 1 there. So at least in the 1, 1 entry, we get 0 minus 1 plus 2, which is 1. All right, well, since it's true for one of the entries, it must actually be the identity matrix. So if you go through the process of actually doing this calculation, you get out 1, 0, 0, 0, 1, 0, 0, 0, 1. And you can show that if you do it in the other order, you get the same thing. You can, if you're doing this in practice, like you've computed an inverse and you want to guarantee that it's actually the inverse, just spot checking a couple of entries is usually enough to tell you if you've done it correctly or not. So I might check that entry to make sure 0 comes out. Yep.
Does it matter the order you multiply A inverse times like the B vector?
What do you mean?
Like the AX equals B?
Okay, I'm getting right to that after I do this.
Okay.
It absolutely does. That's a good question. So let me just check this entry real fast to make sure 0 comes out of it. Which row and column should I multiply in order to check that one? Second row of this matrix, third column of this one. So if I take this row and I dot it with this column, I get 6 minus 3 minus 3, which is 0. Okay, so I believe that if I checked 2, well, 2 of 9, I must be correct, right? Okay, so the idea, I just did it, the open thing. So let's look at AX is equal to B. What that says is, I'm going to write down a matrix problem. So x minus y plus 2z is equal to 1 2 minus 3y plus 3z is equal to 1. I'm just making up a problem involving that matrix, okay? And this is 2x. 2x. And x minus y plus z is equal to 1. So I've made up a system of equations. The way we learned how to deal with this system of equations in the last chapter was we wrote this into an augmented matrix. 1 minus 1, 2, 1. 2 minus 3, 3, 1. 1 minus 1, 1, 1. And then we row reduced it to find the answer, right? What I'm going to suggest, so first of notice, that coefficient matrix is the matrix A that I wrote down over there. So another way that we could have written this problem is like this. I could have written this as 1 minus 1, 2, 2 minus 3, 3, 1 minus 1, 1, times the vector x, y, z is equal to the vector 1, 1, 1. This is the other formulation of the problem. Matrix and vector version. So if I had the inverse, and I do in this case, another approach to solving this problem would be, if that was a number, this is an algebraic equation, I would divide by this. But division doesn't make any sense with matrices. So instead, I'm going to multiply both sides by the inverse of that. So if you took the inverse, which is b, 0, minus 1, 3, 1, minus 1, 1, 1, 0, 1, and you multiplied it by the original problem, and then this, the original vector 1, 1, 1. Oh, I still need the x, y, z. So what I've done here is, and this is to Aiden's question, I'm multiplying on the left by this matrix because I need the matrix and its inverse to touch each other, right? If they're not next to each other, if they're not juxtaposed, then this inverse doesn't work. Right now what I have is a matrix times its inverse. They're next to each other, and so when that happens, this is going to be the identity matrix. The result of this calculation, the way I've written it down, is that a matrix times its inverse is the identity. 1, 0, 0, 0, 1, 0, 0, 0, 1 times x, y, z. And on the right-hand side, that's pretty easy to compute. So what, 0 plus negative 1 plus 3 is 2. And 1 minus 1 plus 1 is 1. And 1 plus 0 minus 1 is 0. And so x, y, z is equal to 2, 1, 0. If I had the inverse, it's very easy for me to solve the equation with matrix multiplication instead of row reduction. Now, the question I got asked was, does it matter where you put the inverse matrix? And the answer is, if I had a matrix system that looked like AX is equal to B, and I right multiplied, so suppose you took this and you decided, I'm going to chuck A inverse on the right. Remember, matrices don't commute when they multiply. You do things in matters. Does this multiplication even make any sense? This matrix is n by n. This vector is n by 1. This matrix is also n by n. So I have an n by 1 vector times an n by n matrix. This isn't even defined, right? And I can't slide the A inverse past the x because matrix multiplication doesn't commute. So when we're solving a matrix system like this, basically the only choice we have is to left multiply, because the variable is trapped on the right. Okay, so we can play all kinds of algebraic tricks with this.
Multiplication wouldn't work the other way.
What's that?
Multiplication wouldn't work the other way.
You can compute A inverse A and A inverse, but the
B inverse A.
it also still doesn't. Yeah, none of this. Yeah, this doesn't work either, right? Because again, this is n by 1 and this is n by n, so the matrix, the multiplication is ill-defined.
Got it.
Right. Yeah, so this is basically, you have to be really careful about the order that you undo things in when you're doing matrix mathematics. Okay, So I guess the idea here is, if we could find that object, it would be awesome. How to get it, we're going to do a little bit more of the structure of inverses, and then I'll show you the algorithm. So I guess the first thing I want to say is we have a couple of theorems here. So one theorem is, if A is n by n, and A is invertible, oh, I need to define that first. I did this in the last section too. Let me make one definition before I state a theorem. So let A be n by n. So A is square. If A inverse exists, A is called non-singular or invertible. If A inverse does not exist, A is called singular. So let me write down some examples of singular matrices. This is very different case from numbers, by the way. Every number except 0 has a multiplicative inverse. Many matrices do not have inverses. A massive complication in matrix algebra. So, for example, the matrix 1, 0, 0, 0 is singular. That is, it has no inverse. The matrix 1, 1, 2, 2 is singular. The matrix 1, 1, 1, 1, 2, 3, 0, 1, 2 is singular. And as you go, it gets harder to tell, right? It's probably pretty easy to guess that's singular because there's so many zeros inside of it. And you might look at that one and say, well, you basically just took an equation and then a multiple of the same equation, so that must be what's happening. But the more stuff you pile in, the harder it is to detect if a matrix is singular. So what we're going to do next time is we'll learn the main tool that's used to detect singularity, which is the determinant of a matrix. So determinants are one of the main tools you use to decide, is the matrix got an inverse or not? We don't have that yet. Okay. For now, we're going to write down a version of what's called the invertible matrix theorem that actually is going to give you a bunch of conditions for telling already with what you know if a matrix has an inverse or not. And that's going to lead to our method for finding the inverses. Okay, so here's a theorem. And there's two parts to this theorem. One I've already shown with the symbolic algebra, and the second, which is pretty important. If A is invertible, if I say something's invertible, it is necessarily a square matrix. Inverses don't exist for things that aren't square. If A is invertible, then AX is equal to B has the unique solution. X is equal to A inverse B for any vector B. Essentially, that theorem says algebra works. If a matrix is invertible, you can do algebra with it, exactly like we would with numbers. So that leads me to one of my favorite exam questions in this part of this class, which is I'm going to state something called the invertible matrix theorem, which now has 6 equivalent conditions for a matrix to have an inverse. By the time we're done with the class, there'll be like 14 or 15 of them. And my exam question is something like here's the invertible matrix theorem. Write down at least 10 conditions for a matrix to be invertible. It's a fun question. Oh yeah, it's so fun. The thing is that they're all useful. This is one of these theorems that's like, this is one of the main structure theorems of linear algebra. Invertible matrices. I mean, if I was going to do that to you, I would let you know it was coming. And then everyone just goes and learns the theorem, right? But The invertible matrix theorem says the following. This is version 1 because every new idea we learn in linear algebra, the invertible matrix theorem will get more parts. Let A be n by n. So A is a square matrix. Mathematicians will now say the following are equivalent. And what that means is all of these conditions will be true simultaneously or they will all be false simultaneously. There's no middle ground. If one of them is true, they all are. If one of them is false, they're all false. 1. A is invertible. 2. A is row equivalent to a matrix with a pivot in every column. Three. A is row equivalent to the identity matrix. So if you keep going, put it all the way down into reduced square echelon form, you can row reduce it to I.
And does there has to be a pivot in the last column? Or?
So remember, A you should think of as being a coefficient matrix. So it's every single column has a 1 inside of it. It's a square matrix, every column has a pivot.
Okay, so every column.
Yeah, every column.
Okay.
Right? 4. So these conditions are annoying to say, and so the number of pivot columns of a matrix we write down as the quantity rank. The rank of A is equal to n. That is just the mathematical reformulation of the idea. It's just, what is the number of pivots of A? If you reduce A, how many columns have pivots inside of them? That's what the rank tells you.
Wait,
Yep.
for this one, is that saying that they're like A can be
This one?
I
It means that the RREF form
is I?
of A is I.
So it reduces to
It reduces all the way down to the identity matrix.
Okay.
Yep. All right, 5. AX is equal to 0 has only the trivial solution. X is equal to 0. 6, essentially what that means is there are no free variables, right? This is a unique versus infinite. One answer versus infinite answers. If every column is a pivot column, then there can't be any free variables, which means there's only one answer. And the final condition is AX is equal to B. Has a unique solution for any vector B.
Why did they write it out so many different ways? Because I'll just say you're writing a pivot.
The idea is that in a lot of cases when you're working with matrices, there's a specific type of question that you're interested in. So if I'm studying functions that are, like say I give you a giant data problem, and you want to know, is every piece of data that I've given you necessary? One way that you could check that would be row reduce the matrix to the identity matrix, right? Or, hey, that matrix is invertible, so all the columns mattered. It gives you a way of moving back and forth between really different kinds of problems. So, for example, if you were solving AX is equal to B, but you knew the matrix was invertible, you could just multiply both sides by A inverse. If you knew that it was not invertible, then you need to row reduce this thing and you expect an infinite number of answers. So we haven't seen a lot of the different contexts where all these bits of this theorem matter yet, but every one of these is used in a different context. So it basically lets you change. One of the main types of this sort of math is you write a problem down, it's really hard to solve, so you change your perspective, and this theorem is a perspective changer. And if you're having trouble writing all this down, this is in the note page that I post online. Okay. What we want to do now, so we've been sitting up here talking about how awesome inverses are and how they're useful and you can solve equations with them. I haven't told you how to find one yet, so we should probably find an inverse matrix. I sort of feel like I should give you the cheesy, last class I gave him the big theorem and then I showed him the cheesy one. I guess maybe I'll show you guys the cheesy dude first. So if A is 2 by 2, it's easy to find the inverse because there's a formula for it. If A is a 2 by 2 matrix, so if A is A, B, C, D, then A inverse is 1 over the determinant of A times D minus B minus C A. This only works for 2 by 2 matrices. If you like this as a more written out formula, AD minus BC times D minus B minus CA. So we can implement that really fast. Let's look at A is equal to 1, 2, 6, 8. That formula says A inverse should be equal to 1 over 1 times 8 minus 6 times 2. And then we're going to have an 8 and a 1, and we'll negate these entries with a minus 2 and the minus 6. And that gets us 1 over negative 1/4 times 8 minus 2 minus 6, 1, which is minus 2 1/2, 3/2, and minus 1/4. And we can verify that. Often when you're working with problems like this, it's actually pretty fast just to verify that you actually do have the inverse here. So let's check. 1, 2, 6, 8 times minus 2, 1/2, 3/2, minus 1/4 is equal to, okay, negative 2 plus 3 is 1, 1/2, minus 1/2 is 0. Oh, sweet, okay, it worked. So I'll just ignore the rest of the calculations there. Okay, unfortunately, while this is a very fast way of doing this, it only works for 2 by 2s. And as far as I know, there's no method that this generalizes to. If we're going to do larger matrices, and in many cases matrices that we work with in practice are enormous, I need a more general method for finding inverses. And as much of a chicken and egg problem as it sounds like, the method that we're going to use to find inverses is row reduction. So I know I made a big deal of like, oh, we don't have to row reduce because we can multiply by the matrix, but the problem is to find the inverse, we need to row reduce. So in practice, what happens is you row reduce to find the inverse, and then once you have it, you can solve lots of systems with it. And if you don't need to find lots of solutions, you just row reduce the first time. So practical linear algebra is hard. All right, so before I actually show you the full algorithm, I've got to show you this. So I'm going to remind you about how matrix multiplication works. And if you're an engineer or applied mathematician, this should delight you, because suppose that you had a matrix A, and I'm going to write A as row 1, row 2, row 3, and a matrix B, which I will write as column vectors, V1, V2, and V3. Okay. The absolute laziest applied math way of doing this is to say, well, A times V1, AB is equal to A times V1, V2, V3. What I'm showing you now is an example of something called block multiplication. Block matrix multiplication. And as a block matrix, this is 1 by 1. And this is 1 by 3, so obviously I can just multiply them because it's a 1 by 1 times a 1 by 3. So I can scalar multiply the A in to get AV1, AV2, AV3, right? Just symbols. That actually works, by the way. This is a one way of thinking about, this is equivalent to our definition of matrix multiplication. But the idea here is that if you actually wrote down A in this row form, and then you multiplied it by V1, V2, V3, and you went through the process that we did when we defined matrix multiplication, you would get a 3 by 3 matrix out the other side, where each entry looked like the dot product of one of these rows with these columns. So row, I'll just do the first column here. Row 1, V1, row 2 dot v1, row 3 dot v1, and then row 1 dot v2.
V1 and V2.
3, row 2 v3, row 3 v. I'll fix it.
And the first.
But if you think about it for a second, row 1, row 2, 1, 3, dotted with the vector v1, v1, v1 is a v1. And row 1, row 2, row 3, dotted with v2, v2, v2 is a times v2. And this times this times this is a times v3. So one way of thinking about what matrix multiplication is doing is you're just taking the columns of B and multiplying by the matrix A. Now, why? Why would you care about that? This is going to be what leads us to our method for finding inverses. So suppose that I had A inverse was equal to the identity matrix. And just for the sake of argument, let's call this 2 by 2 for right now, just to make it easy to see what's happening. So what I'm looking for is the matrix A inverse. Suppose I know A and I'm looking for A inverse. I'm going to let A inverse, and I'm going to write it in column form as V1, V2. If I could find V1 and V2, I would know the columns of A inverse. And that would say A times V1, V2 is equal to, okay, but the 2 by 2 identity is 1, 0, 0, 1. And by the argument I wrote right here, A times the matrix V1, V2 is A V1, A V2 is equal to 1, 0, 0, 1. And so if I want to find the inverse of the matrix, instead what I could do is I could figure out the solution to this problem where A V1 is equal to 1, 0, because that first column of this matrix has to be equal to the first column of this one, and the second column of the matrix has to be equal to the second column. So now I've got two problems to solve, make my life harder. I want to solve AV1 is equal to 1, 0, and AV2 is equal to 0, 1. And of course, the only tool I have to do that is row reduction. But notice, if I'm going to solve this problem with row reduction and this problem with row reduction, the steps I use to row reduce A are the same in both cases. I'm still going to start with A and row reduce it. So there's no reason why I can't just chuck both of these output vectors into a matrix and do it all at once. So what I mean is, instead of solving AV1 is equal to 0 and then going back and solving AV2 is equal to 0 with the same steps, why not just do, I'm going to put an A times, think about this, right? I could do A, and if I augmented that with the matrix 1, 0, 0, 1, so I'm going to take the matrix A, which is the coefficient matrix, and I'm going to augment with both solutions that I'm looking for. It's like I'm keeping track of the two problems at the same time. This problem solves for V1, and that problem solves for V2. So the algorithm here is, if I want to find the identity matrix, the algorithm, I'm going to put the matrix I want to find the inverse of on one side of an augmented matrix, and on the other side I'm going to put a giant identity matrix, same size. And then I'm going to row reduce, and when I finish with the identity matrix on this side, what shows up here is A inverse. If you want a more concrete explanation of what's happening, really what you're doing is, and if you guys don't like abstraction, cover your ears for a second. So what you're really doing is you're taking A inverse is equal to I. Every row operation is actually multiplication by a special matrix called an elementary matrix. So each row operation is actually a matrix multiplication. So every time you do a row operation, you've actually multiplied A by a new matrix, E. And if you do a second row operation, you multiply by another matrix. suppose it took 3 operations to reduce A to the identity matrix. E2, E1, E3 times A inverse is equal to E3, E2, E1. I did the same thing on both sides of the equation. If now I've landed at the identity matrix, this just says A inverse is equal to E3, E2, E1. So the inverse matrix is actually you just pile up the matrices that did the row operations and you get the inverse. And you can turn your ears back on if you don't like abstraction. If you guys want to see this done in more detail and you like the idea of being able to concretely say what's happening, you come to office hours, I will show you what these look like, and that will basically prove that this inverse algorithm works. Okay, so let's do the same problem we did before for that matrix of that little 2x2, but let's do it with this algorithm instead. Okay, so as an example, let's look at, what was the matrix? 1, 2, 6, 8. And I'm going to augment it with the matrix 1, 0, 0, 1. This is A, and this is I. And now I'm going to run the row reduction algorithm. I'm going to row reduce it until that thing is the identity matrix. If I ever hit a step where I have no pivots, I stop and it's not invertible. But if I can row reduce the left-hand side to the identity, then the right-hand side will be the inverse. All right, so let's see. So if you want to know the steps here, if I take row 2 is equal to row 2 plus negative 6 times row 1, you'll get 0, minus 2, minus 6, since it's minus 4. Minus 6 times 1 is minus 6. Minus 6 times 0 is 0. Step 1. I think I did the right. Negative 6 row 1 plus row 2. Now I'm going to scale row 2 by negative 4. 1, 2, 1, 0, 0, 1, 3 halves, 0. Oh wait, there's a 1 down here that I blew, isn't there? Just 1. Oh, but now it's a 1/4. Negative. Sorry, there's a 1 here I should have dragged down because 1 plus 0 is 1, not 0. Okay, now I'm going to use this position to get rid of the 2 up here. I guess I should write down the row operations. This was row 2 becomes row 2 plus negative 6 row 1s. This step was row 2 gets replaced by minus 1/4 of row 2. And now for the last step I'm going to do row 1 becomes row 1 plus negative 2 times row 2. To get rid of that 2 right there. And I think you end up with, let's see, 0, 1, 3 halves, 1/4 with a negative in front of it. Row 1 plus negative 2, row 2, that's a 1. 2 times negative 2, 2 plus negative 2 is 0. 1 plus negative 3 is minus 2. And 0 plus a half is a half. We get the same answer. So the idea is, this thing that I did right here, where I started with A and augmented with I, and then I row reduced to get the identity and A inverse, this method works for matrices of any size. Any size matrix this will work for. A question that you might have right now is, well, what are we actually going to be expected to have to do on an exam, right? Like on the homework, it's one thing for me to say, do these little examples. This would be a reasonable way, the problem like this, would be a reasonable way for me to check simultaneously if you understand inverses and if you could do row reduction. Because I could just give you a tiny problem and say, find the inverse of a 2x2 matrix using row reduction, and there's not much to do here, right? But it would check your ability to hand row reduce, and then when you get down here, I could say, verify that your answer is the inverse, which means do the multiplication, where you show some steps and you don't just write, well, it must be, so put 1, 0, 0, 1. I know you guys are all really smart and you can do that, but... Okay, so in practice, I will point this out before I do some symbolic algebra here, which will be our last thing for today. If you actually want to do this without having to go to your calculator, or you don't have a calculator, if you go to Wolfram Alpha and you want it to row reduce a matrix for you, you could just go to Wolfram Alpha and input the matrix in this brace form. So if you go to Wolfram Alpha and you just put that in the entry field, which is the array that has 1, 2 in the first row and 6, 8 in the second, and hit enter, it will produce the inverse of the matrix for you. If you got a fancy TI left over from your high school days, you can use that too. If you've ever used the matrix command before, and there you're looking for something called RREF. Okay.
Is there a way to find this comment? Like, what kind of inverse is?
Yes. You can either, so if you were in your TI-84, you could either RREF this matrix, and then the last bit will be the inverse, but there's actually just an inverse command inside there. Okay, so check your answers. All right, so the last thing I want to point out is inverses satisfy certain nice algebraic rules. So if A and B are both invertible, and the same size, then the inverse of the inverse is the original matrix. The inverse of a product is the reversed product of the inverses. That's kind of a fun one to show, right? Because what that says is if I want to undo AB, I should multiply it by B inverse A inverse. And you can check that. AB times B inverse A inverse. These matrices are juxtaposed, and so B times B inverse is the identity matrix. The identity times anything is itself. And A times its inverse is the identity. So the matrix that undoes the matrix AB is the matrix B inverse A inverse. And then the last step is these are also compatible with transposes. So if I have a transpose of a matrix and I want to calculate its inverse, I just calculate the transpose of the inverse. They're like power rules for matrix operations. A transpose inverse is A inverse transpose. Okay. So that sort of finishes the content for the day.